Give me a second. I need to flip. How do I flip? Transform, rotate, flip horizontally. Can you guys see it? I'm just fixing a setting, guys. I'm not doing the salute, okay? I'm just fixing a beep, boop, 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 boop. Okay. It's fixed now. Cool. What the fuck? Bro, I'm not. I don't give a fuck, nigga. Ooh. Ooh. Oh my god, bro. Oh my god, can a nigga do his job, please? Please. Okay, whatever. Whatever. Man, I had like a crazy dream the other day. I mean, today, I guess. I was in a synagogue and I saw Mohawk. Is that how you say it? Mohawk. No, I did not see him. The Mohawk. Yeah, I saw this guy, man. It's gonna fucking scare me now. I saw this guy. I tried to like run away from him. Yeah, the bull-headed man. Crazy. I saw I don't know, scary stuff. Scary, huh? Yeah. I need to shave my beard. I look homeless. Okay. I need to cheat my code. Oh shit, I forgot. What's my thumbnail? Shit, the whole point was like to get my thumbnail on. Why you guys not watching me, man? Such a insightful stream. What the fuck, bro? Lead code, come on, man. What? You guys are so slow. So if this is the starting line of the code, and for else balanced, how do I find if it's balanced? Height balanced, so I need to go check. நாலு மாசம் 6 மாசமா பண்ணிட்டு இருக்கேன் மாமே. What even is this question?
Hey everyone, welcome back and let's write some more neat code today. So today let's solve the problem balanced binary tree. We're given a binary tree and we want to determine if it is height balanced. What exactly do they mean by height balanced? Well, it's defined by saying that for every single node in the tree, if we take the left and right subtrees of this node, the heights of these left and right subtrees will differ by at most 1. So in here you can see, taking a look at the root node, it has a left subtree. What's the height of this left subtree? Let's call it 1, right? Because there's one node in the left subtree. What about the right subtree? What's the height of this right subtree? Well, it's 2, right? We can determine that just by looking at it. So then the left subtree has a height of 1, the right subtree has a height of 2. The difference is at most 1, right? Because if we take the absolute value of the difference, we get 1. So we'll say the difference is 1. So we just did that for the root node, but we have to do that for every single node to make sure that the left and right subtrees of every single node differ by at most 1.
What am I doing? I don't want to do this. It's too much. Too much work. What are you doing?
Hey guys, it's been a while. 1 year ago, I joined one of the best AI startups in the world, and although I don't regret anything, it cost me almost everything. I went from doing sports 6 days a week to 0. I left behind my family, girlfriend, and friends in Germany to move to Tokyo. And I left you guys hanging. I went from creating 2 videos a month to, well, 0. It was tough, not gonna lie, but after a few months, things started to change a bit. And after 1 year, they changed even more. So in this video, I'll give you a short life update on what I've been doing and most importantly, what I'll be doing in the future.
Yeah, I just want to punch this guy. No offense. I just want to like... See this? I just want to like... I don't know. Something about your build, man. It's just like... I don't even know what to say. I don't even know what to say, mate.
I gave 2 hours daily to DSA, system design. Best decision ever.
What even is system design?
This title addresses 2 of some of my favorite things. First thing is productivity. I'm aiming to or try to do something every day. This YouTube video, for example, is part of it. And learning about DSA and system design and anything that is computer science.
If you want to level up from a junior developer to a senior engineer, or learn.
Do you want to level up from junior dev so that you can build scalable apps or maybe get a 100K pay bump by passing your system design interview round? Well, you're going to need a box of neat codes, 20 essential system design concepts, which include networking, API patterns, databases, and more, all of which are covered more extensively on neatcode.io. To start, let's say you have a single server, which is accepting and fulfilling requests for your application. But now we're getting more users, so we need to scale it. The easiest thing to do would be to add more resources like RAM, or maybe upgrade your CPU. This is known as vertical scaling. It's pretty easy, but it's very limited. A better approach would be to add replicas so that each server can handle a subset of requests. This is known as horizontal scaling. It's more powerful because we can almost scale infinitely, and we don't even need good machines. It also adds redundancy and fault tolerance because if one of our servers goes down, all of the other servers can continue to fulfill requests. This eliminates our previous single point of failure. But the downside is that this approach is much more complicated. First of all, how do we ensure that one server won't get overloaded while the others sit idle? Well, for that, we'll need a load balancer, which is just a server known as a reverse proxy. It directs...
I wanna beat some people up. I'm going crazy. What am I doing? Oh man, I need to like train MMA tonight. Fuck. It's so boring. This shit is so boring, man. This shit is so boring. Oh my god. Oh my god. What should I do? let me get my notebook, learn some statistics.
This video is sponsored by Brilliant. Here we have a rectangular function, and here's its associated Fourier transform, just a sinc function, which is found through this equation here. What makes this integral kind of scary looking, especially to people first learning this, is of course the exponential term, since it's got I.
How should I go about doing this? Oh my god. Oh my god, it's so much to learn. Oh.
In it.
Oh, if we do Nyquist again, Nyquist, the maximum thing that my 16,000 samples per second can represent would be 8,000 cycles per second. And we have a problem, because in my original audio of 24,000 samples per second, with my 12,000 max, I was covered because I know 10,000 was the most in my data. But now that I've downsampled my audio from 24,000 to 16,000, the max I can represent is 8,000, which is underneath the 10,000 that I need. So this 10,000, basically all the frequency information between 8,000 to 10,000 hertz that was in my original audio will get aliased.
Griffin.
And so you end up losing that frequency information because your signal just can't contain it anymore. So it has to go somewhere, and so it gets aliased down. And so let's go ahead and take a look at what that looks like. So what we're going to do is we're going to create a audio file, or basically a sinusoid, just like we did before. And what we have here is and this would be 200. We have a 200 samples per second audio, right? So if it's 200 samples per second, I know the maximum thing I can represent is 100 cycles per second. So I know it's 100, but I picked 40. So 40 is under 100, so we're good to go. So I go ahead and create that sinusoid. And what we're going to do is just apply the Fourier transform to it, just like we did earlier, nothing new. So we're going to go ahead and provide the Fourier transform, everything same as before, nothing new. And now what we're going to do is downsample the audio, right? We're going to downsample. So we're going to do a downsample factor. It's going to be, let's say, a factor of 4. Yeah, let's do a factor of 4. So that means we're going to go from 200 hertz, downsampled by a factor of 4. So it'd be 50 hertz. So we have 50 samples per second. But if we have only 50 samples per second, so this is going to be 50 sample per second, which means that the maximum cycles per second that I can represent is half. That'd be 25 cycles per second. The problem is 25 cycles per second is less than the 40 that I have in my original audio, right? The original signal. So let's see what happens to that. So what we're going to do is downsample our audio. That's just going to be T low is going to be equal to T high. So we're going to downsample both my time. So we're going to take every other time step and our data itself, T high, and we're going to do downsample factor, right? We're going to skip every step. And then similarly, we're going to do Y low is going to be, and this is Y basically, low is downsample. It's just going to be the Y high, again, downsample factor. Right, so I've gone ahead and downsampled everything by a factor of 4. And then just like before, we're going to go ahead and apply our Fourier transform to the downsample data. Right, so go ahead and apply the Fourier transform, get the frequencies of the downsample data. So there we go. And now let's go ahead and plot it. So again, I'm not going to make you watch me create some plotting functions. So here's my original signal. I had, and this shouldn't be 80 hertz, this should be 40 hertz. Okay? There we go, 40 hertz. So I have 40 cycles happening in 1 second. But because I downsampled my signal by a factor of 4, now you can see we have 1, 2, 3, 4, 5, 6, 7.
So he's taking the high frequency sound and downsampling
8, 9, 10 cycles happening in the same amount of time because we've downsampled directly by a factor of 4. And here's the aliasing effect. I had a signal that originally had energy at 40 hertz. Now that my downsample signal can no longer represent that information, it gets aliased down. So we can only represent that 40 hertz frequency gets aliased down to here instead. And so this is you losing that frequency information. And why it's really important to keep in mind, what are the general frequencies that your audio is working, that your audio contains, and make sure that when you do any kind of downsampling of your signal, that you still maintain that information in there. So these are just kind of good ideas to keep in mind. Now, what would be interesting here is what if we change our downsampling factor to 2? If we change to 2, that means we're going to go from 200 hertz, right, 200 samples per second. So if we do this to 2, that means we'll only go down to 100 samples per second, right? We're going to go from 200 down to 100 because we only have, which means the highest frequency cycles per second we can represent is half, and that would be 50. Luckily for us, 50 is greater than the 40 we were working with. So we should see no aliasing happening now. So let's see if that's true. And you can see exactly that. We lose some energy, like magnitude, but that same frequency is still represented. So we haven't aliased that information away. Right? All right, cool. So that is your should be the main takeaway about aliasing. So let's just keep moving. Like I mentioned, at the beginning, the whole point of a Fourier transform is to basically undo mixed paint, right? And so what happens if you take a couple of different signals with 3 different frequencies? We have a sinusoid at 5 cycles per second, 20 cycles per second, 40 cycles per second, and we just add those signals together and then do the Fourier transform. Well, basically the same thing. Here's the sum of your sinusoids, and the Fourier transform is able to identify energy at 5 hertz, energy at 20 hertz, energy at 40 hertz. Right? So we're able to find those frequencies here. If we add another one, let's say we add one at 250, then we'll end up with kind of a signal that looks like this, but we have 5, 20, 40, and then here we go. We have one straight at 250. So the Fourier transform again is able to identify the energy at the different frequencies available in our signal. And so that's the fun part. Now, of course, if we do a Fourier transform, and the Fourier transform goes from the time domain signal, where the x-axis is time, to the frequency domain, which the x-axis is frequency. If we can go in one way, then we should be able to go the other way, right? The inverse transform. And this is as simple as just doing the inverse transform, which I can just go ahead again. Same code as before, adding together a bunch of sinusoids, do the Fourier transform, but after you do the Fourier transform, do the IFFT, inverse Fourier transform. So in the exact same way. Here you go. You have a signal, you take its Fourier transform, and then you take its inverse Fourier transform, and these two signals should be identical to each other. And there we go. Now, here's the problem with a Fourier transform. And let's kind of think about it this way. I'm going to apply the Fourier transform to our actual audio. So if you remember up here, we had our audio file. This audio file contains lots of different frequencies, right? Lots of different frequencies. And so what we want to do is apply the Fourier transform to this and just see what that looks like. So I called it audio, so that's what we're going to do. All we want to do is basically this code right here. We're going to apply U to our audio instead. So instead of the sum of sinusoids, let's get rid of that. We're going to do it on our audio. And T is going to be len audio, and we know that our audio is sampled at 16,000 samples per second, so the distance between time, or the, is going to be 1 over 16,000. And so we end up with, and let's change U to audio, and there won't be a T here, this will be range audio. Oh, right, we have to do list range audio, make sure it's an array. Only integers of a single element can be converted to an index. Here, let's just do audio. Here we go. So we have our audio file, just like that. This is our, and this is no longer the sum of sinusoids, so these titles no longer are correct, so let's get rid of that. There we go. So this is the audio file that we were working with, and here are all of the frequencies that are available in that audio file. But this view is not actually all that helpful to us. Like, sure, we have the frequencies, but notice that audio files, unlike the signals we were working with here, because this signal here kind of repeats and it's, it's very repetitive, it's periodic. The audio file, there's clearly some change happening over time. Like in these areas, like the empty areas, we have low frequency, like nothing's happening here, so it's low frequency. In these areas, there's lots of change happening, so this is a higher frequency. And because there's kind of this mix of low and high frequencies and things are changing over time, we lose that because in the regular Fourier transform, we go from the time domain squarely into the frequency domain. Like it's a full conversion to the frequency domain, and the inverse Fourier transform goes backwards. But is there
Inquisition sampling theorem. What does it mean? Nigga, I will fuck you up. Fucking nigger. I think.
In 1982, the fruits of a partnership between Sony and Philips were released to the music-loving public. The compact disc, or CD, was unveiled as the first consumer digital audio format. These 12-centimeter discs could store up to 74 minutes of perfect quality digital audio, and as was famously demonstrated many times over, were immune from liquid damage.
The so-called Nyquist theorem is almost a religious artifact for anyone who has any bit of formal training in digital audio. It's used as a kind of checkmate argument against analog purists who think that 44.1 digital is stair-stepped and doesn't sound good and is low res. Any questioning of the theorem makes you look like an uneducated hi-fi layman normie.
That's what listen, I like drama, like I'm a little bit of a bitch. Okay, I'm a little bit of a queen. I'm a black queen. I like drama.
So that's exactly why
that.
in today's video, I'm going to blow that completely apart and show how what is taught
that's
in
my man,
universities
right
is
there.
completely wrong, and what is regurgitated in the industry about the theorem is a load of twaddle. So I'm going to...
I need to take a piss break now.
assume that most people watching this video have already heard about the Nyquist theorem. If not, the way that it's commonly thrown around in the industry is something like this. You need to have a sample rate double or higher than the highest frequency that you want to hear, and then you're guaranteed perfect fidelity. For example, a human ear hears up to about 20k if you're lucky, and then we can double that and get to 40k, and if we have a sample rate of 40k or higher, then we can hear everything that human ear is capable of hearing in perfect fidelity, and we're guaranteed that because the theorem says so. And if you disagree with the theorem, then you're an idiot. Checkmate. That's basically how it goes in the industry, and that's used to argue with hi-fi guys who are like, yeah, but 44.1, you've only basically got around 2 samples, and it's not high enough fidelity. You get these weird stair steps, and that can't perfectly reproduce the frequencies. What you're talking about, it's so granular. How does that work at all? Vinyl is way more accurate, way more pure, because you don't have these 2 samples at 20k, you've got molecules. And then the digital advocate will hit back and say, no, you don't know what you're talking about, because we use a low pass reconstructive filter and all that stair step stuff goes away. That's just theoretical. Actually, it's a lollipop graph and not stair step anyway, and when we reconstruct that after the low pass filter, we get back the perfect 20k tone. So you don't know what you're talking about, and they will often link a video like Monty Montgomery's great video on this topic, but even that video doesn't give the full story, and it gives more of the impression like the way that it's taught at universities, which in this day and age is unfortunately completely wrong. So if you're a hi-fi enthusiast, an analog purist, and you think that CD quality digital doesn't sound good because it's too low res, then you're wrong. And if you're a digital advocate and you explain digital technology in the kind of way that I've just explained it, then you're wrong as well. Even universities teach this, everyone online teaches it in this way, but it's just really, really outdated to the point where it's just wrong. Even the name Nyquist theorem is wrong. Now, Harry Nyquist published a paper almost 100 years ago now called Certain Topics in Telegraph Transmission Theory. In that classic paper, Nyquist discusses a whole bunch of different things, but one of the things that he is discussing is Fourier decomposition, how all sounds can be broken down into a bunch of sine waves. And the paper is, of course, especially easy to read, as you can see here. But the place where the layman's Nyquist theorem comes from is not actually from Harry Nyquist himself, but rather from Claude Shannon's formalization of what Nyquist said in his 1949 paper, Communication in the Presence of Noise. Now, as you probably guessed, having a PhD in mathematics would help you out reading this paper, but it's not actually that difficult to understand, especially if we only look at the part of the paper that we're interested in terms of what people call the Nyquist theorem today, because he writes about a whole bunch of other stuff. Shannon was an absolute legend in many different fields, but part of his paper writes about exactly what we're talking about here with the Nyquist theorem. So the theorem, as stated in Shannon's paper, is if a function contains no frequencies higher than w, it is completely determined by giving its ordinates as a series of points spaced half w seconds apart. He then gives a mathematical proof of this, but to understand what he means, what's going on there, you have to understand the context of what he's writing about there. The context is he's talking about math. He's talking about a Fourier transform function going from discrete to continuous domains, and he says that we can perfectly reconstruct that by using pulses, and the amplitude of the center of each pulse is simply the sample value, and the sum of all of those pulses becomes the perfectly reconstructed output. And what he's referring to as pulses, he then later defines, and that is what we would refer to today as a sinc function. So it's getting a bunch of different little sinc functions centered at the amplitude, and then sum them all together, and voila, there you go. You have the sum again, which is a perfect equivalent of the original signal. And that is a mathematical theorem, mathematical proof that he does, and it doesn't necessarily refer to what people have in their mind when they think of digital audio. Now, whether that was as clear as day or mud depends on how much you know about math, but you don't really need to understand that. I'm just trying to make the point that what is taught at universities on audio engineering degrees today Ableton Live,
and not what was stated by Shannon's original paper. So I'm going to refer to what people commonly teach and understand about how digital audio sampling works as the outdated method. Now, this is problematic for a whole bunch of different reasons. So let's say the original layman theorem says if you have your sampling rate twice that of the highest frequency you want to sample, then you're guaranteed perfect fidelity. Well, let's say we take a 20k sine wave and we have a sampling rate at 40k. Well, what happens if the sample intervals falls on the zero crossings of the sine wave? Well, now we record nothing. We record silence, because every time we take a sample, it's at zero. So we don't know that there's a sine wave there at all. So the input is a sine wave and the output is silence. So we don't have perfect guaranteed fidelity at all. We have it's nonsense. So that doesn't work at all. What happens if we lower the pitch of the sine wave at 20k slightly down to 19.99 something k? Well, now it's going to slightly shift the phase angle over time relative to the sampling interval. So now we're going to be sampling at the top of the sine wave, and then as it gets lower down to the zero crossing, then it's going to have a lower amplitude, and it's going to get louder again. So we're going to have this fading in and fading out of that high pitch sine wave. So that's not perfect fidelity at all. And sine wave. So that's not perfect fidelity at all. And if we lower the pitching further, it's going to happen quicker and quicker and quicker. The beating will speed up. We'll have a beating effect. Now we'll get quicker and quicker until at some point the frequency is low enough that that beating effect disappears. So now onto the next problem of the outdated method. So all digital audio systems low pass filter the input signal to get rid of the high frequency content that might go above the Nyquist frequency. That is half the sample rate. Because if stuff goes above half the sample rate, then it starts getting mirrored back in to below half the sample rate because of the ambiguity of having less than 2 samples to sample it. So that's called aliasing. It sounds really bad. A lot of people have heard the term aliasing. It doesn't sound good. We want to avoid that. So we need to low pass filter the signal. But let's say we have CD, for example, 44.1 kilohertz sampling rate. Well, half that is 22.05. Let's just say 22. Well, we want to hear sounds up to 20k. So we only have room between 20k and 22k to do a low pass filter to go from letting everything through at 20k and then killing everything at 22k. It has to be such a steep filter, that's just ridiculous. If you calculate it, it has to be something close to 600 dB or more per octave to get down to something like 90 dB attenuation at 22k. It's just way filters. But the dynamic range aspect.
Bro, this is like so left field. What am I even doing?
any kind of middle ground that we can do where we have both time and frequency information? And yes, that's exactly what we're going to do. This is known as the spectrogram. And the spectrogram is known as it's basically like a picture of the audio. And hopefully this will make sense. Before we do it in Torch Audio, we're going to go ahead and do it in SciPy, because SciPy will provide, again, remember, a Fourier transform provides us both the, scroll back up just to make sure, it's a complex number, return a complex number, which means we can get both the magnitude and the phase information. Both of that's available to us. It's just, up till now, like what we're looking at here, all of this stuff is just the magnitude, because typically we just care about the magnitude, about how much energy is there at the different frequencies. Either way,
I'm pretty sure I'm following this guy. Still not. Okay, why did I dox my friends? Fuck. I shouldn't do that. I just get carried away sometimes. I'm sorry, my friend.
let's go ahead and take a look at what this produces. When we apply the Fourier transform, the short time Fourier transform, so the short time STFT, short time Fourier transform, produces something known as the spectrogram. And the spectrogram we'll talk about a couple things in just a bit, but it produces both the magnitude and the phase. But notice here that things are a little bit different, where we have a time and a frequency axis, right? Time and a frequency axis. Whereas opposed to before, we just had frequency, or we just had time, and we just had the magnitude along, our y-axis. And so because we have time and frequency at this beginning, once you get really, there is the number of samples per segment, and then the 2000 our signal that we're working with. We take the chunk that we have, and we're going to saying I want to do 0 to 20,000, right? Our frequency decibel values here. And just like before, if we change this to spectrogram, it's going to be transform audio, or we take our audio, apply that transform to it, and let's go ahead and plot it. And when we plot it, you end up with something like this, which obviously is not very helpful to look at. Like, there's not really a lot of information here. And that's because we're looking at the raw amplitudes. And it's very common to take the raw amplitudes here and scale it, typically log scale it. So what we're going to do is convert it to decibels. And so decibels, very clear formula, we can just take the log of this thing and multiply it by 20 and we'd be good to go. But let's just go ahead and learn a couple of the transform decibel values here. And just like for human hearing, human speech, this is essentially the power law of perception. So there's a lot of ways to think about it. Let's think about it in terms of dot sign. It's not as big of a difference. It doesn't feel as big of a difference. And let's do another one. Let's do 2500. Sorry, it's a little loud. And then we'll do 2700, so it's a 200 increase. It's a very little bit of increase because perceptually it doesn't seem like much more. And so this is exactly what the MEL frequency, the MEL scale does. It puts less of an increase in changes in higher frequencies. And so our first goal, right, again, is here. So all of our frequency XX, right, our short time Fourier transform actually is a text-to-speech model. So text-to-speech and then repeat when converge. Again, we're going to take a look at a little bit of the math and the implementation in the future of how we actually build this, but we're just going to basically do a bunch of iterative short time Fourier transform, take an inverse short time Fourier transform, keep going over and over again until our phases converge. The reason this actually works is because, again, of that overlap add method. Because if I take a short time Fourier, if I take a Fourier transform of this chunk right here, and then this second chunk right here, and we'll end up with a small bit of overlap between the two. And if we have an overlap, regardless of how many Fourier transforms and short time Fourier transforms that we take, and inverse Fourier transforms, no matter how many times you go back and forth between the time domain and the frequency domain, these values have to be the same. And so it's a constrained optimization, essentially, where we want to basically keep taking the transform, the Fourier transform, and the inverse transform over and over again, and ensure that these values end up converging to be the same, which will only happen when the phases align. So that's kind of a high level of why it's working, but we'll look at that in more detail later on. So for us to do this, the Griffin-Lim algorithm actually only works directly on the original later on. Here is our negative frequency, and the other half of the positive frequencies. We typically only care about the positive frequencies, which is why this has 512 plus 1 for the DC term, right, 0 frequency. So we have 512 plus 1, so 513 frequency bins that are had. Because all of the other frequency bins that would be on the other half, right, they keep going in the negative direction, they would just be exactly the same as this. It'd just be a reflection of the same data, just on the other half. And which is less interesting to us, right? We don't really care about the negative frequencies, we just have the positive frequencies. And so that's where this 513 comes from. And so that will make more sense why we need that right here. So now that we have this MEL spectrogram, what we want to do is convert this MEL spectrogram back into the original spectrogram. So how do we do that? This is going to be inverse MEL scale transform. It's going to be et.inverse MEL scale. And this is going to need a couple pieces of information. First, STFT. How many frequency bins are there? Well, we have 1024, but we only will be computing for the positive ones. So that's going to be 512 plus 1, 513. So that's why we have 513 here, because we only want to keep the positive and the zero frequency term. And then how many MELs do we have? N MELs? Well, we set that ahead of time, right? We set 128 MELs, so it just needs to know that, the signal coming in has 128. And then, of course, we provide the sample rate is the sample rate, and then we provide the MEL scale that we use. In this case, we use Slaney, so we're going to let it know Slaney here. And this will go ahead and invert our spectrum. So we're going to go from MEL spectrogram to regular spectro. We can finally go ahead and do reconstruct waveform, and we know the rate is 16,000. And play back.
A distinct promise of 100 pounds was made to him if he would have the child ready to hand over to Trevel.
Okay, so not bad. It sounds a little robotic, right? But we did reconstruct something. And this could be an artifact of the lack of the one-to-one mapping to go from MEL.
That is a basic reconstruction of
A distinct promise of £100 was made to him if he would have the child ready to hand over to Trevelyan on Trevelyan's arrival in England.
Back to linear spectrogram, and also back of the one to.
Trevelyan.
Okay.
Pounds was made to him if he would have the child ready to hand over to Trevelyan.
Okay, it's not bad. It sounds a little robotic, right? But we did reconstruct something. This could be an artifact of the lack of the one-to-one mapping to go from MEL back to linear spectrogram, and also, of course, the approximation errors from an iterative algorithm of going from our spectrogram to our audio itself. Let's listen to the original one again. That was just regular. I think it was called audio, so let's just do that.
A distinct promise of £100 was made
That's
to him.
original audio. And so this method is okay, but actually not all that much used these days. You're better off using something known as a neural vocoder. So Griffin Lim can create a reasonable approximation of magnitude spectrograms to audio, but it's not as good as deep learning based methods. So there's a lot of deep learning methods out there, like Hi-Fi GAN is one we'll implement one day in the future. And in Hi-Fi GAN, you end up basically learning a neural network to take a MEL spectrogram and produce the audio directly. And these are significantly higher quality than something Griffin Lim could produce. But either way, let's go ahead and just do a summary table here, just so you can see the flow between all the things that we did. So what we normally start with is a waveform, right? A waveform. Right, that's our original data. And there's two ways we can process this. Either one, we do a Fourier transform, right? Fourier transform, and this is going to produce a frequency.
Speech
recognition. And the waveform is time domain, right? Time domain data, and this is going to produce frequency domain data, right? Fully frequency. So in this case, we've lost all of the temporal information, and this is not really a pathway we normally take, especially for speech processing and audio processing for neural networks, because we want to have a mix of time and frequency domain. So let's go ahead and get rid of this because we're not going to really. Hey everyone, today we will be looking at the CTC loss, or the connectionist temporal classification loss, which is super popular for automatic speech recognition, but some other applications as well. Before I go ahead and start though, I want to cite a couple of places that I would recommend taking a look at. The code we'll be writing this in a little bit is based off of this implementation right here from Vadim Kantarov, sorry if I butchered your name, but it'll essentially be a rewrite of this, with just a little bit more explanation of what's going on. So go ahead and start this repository because it's awesome. And also, I would recommend giving this a read. This is a really incredible blog post giving a really good idea of what is going on in the CTC loss, and a lot of what you see.
Connectionist temporal classification, CTC. From scratch. Okay. Audio recognition, ASR from scratch. This is gonna be paper review. Let's reproduce. Okay. Basically, not much going on. I need to eat some food. It's almost 1 hour of studying. I think not even. Not studying, but let's see what is going on. Yeah, 40 minutes. Why not? Give me a second. What else he got? Let's build our own my
Hey everyone, today we will be implementing the automatic gradient system. Hey everyone, today we are going to be starting our actual implementation of the MyTorch architecture. So this is going to be a fully functioning deep learning framework. It's a continuing project, so I'm going to keep adding stuff to it. But our goal is to implement all of the core stuff that we care about when it comes to training neural networks. So one of our previous videos going into this was essentially implementing a GPT-2 type model with nothing, right? Just NumPy. So we basically, or essentially CuPy. So we trained a transformer model with nothing but CuPy, which means we had to implement the forward pass, the backward pass, all. Hey everyone, today we will be...
I know this is eating food and learning is like the worst way to do it, but I'm gonna do it. I'm gonna do it off stream, by the way. Yeah.